Welcome to the conservation of energy. Energy is one of those things that is conserved. That means that it stays the same. The amount of energy in the universe stays the same. It can change from one type into another type, but the amount is always constant. We know that if we drop an object from a height, that the gravitational potential energy is turned into kinetic energy as it falls. When you are halfway down, half the energy has been transformed. When you're all of the way down, all of the energy has been transformed. In a situation where you are overcoming something called a resistive force, some of the energy is lost to the surroundings. It is still conserved, but some of the energy goes into non-useful forms. So if you have a rope and you're pulling a box with force F, and the box begins to move at a constant speed, then what's happening is that you are overcoming a resistive force of friction acting in the opposite direction. It is acting to try to stop the box from moving. You are pulling with a force that is equal and opposite to the friction, and so the box moves at a constant speed. The net force is zero. The same situation occurs with vehicles. When you have a driving force on the engine, moving the vehicle forward, you also have a drag force balancing this, and the car can reach terminal velocity. Where the forces balance. And the resistive force in this situation is drag. Previously, it was friction. Friction is a resistive force between surfaces that are moving past each other. Drag is a resistive force when an object is trying to move through a fluid like air or water. Here is another type of problem. We have a box at the top of a slope, and that box will slide down to the bottom of the slope. As it slides down, the movement is in the opposite direction to the friction between the box and the surface of the slope. The force balancing this is the component of the weight that is parallel to the slope. We start off with gravitational potential energy, and as the box moves down the slope, it gains kinetic energy. But because there is a frictional force, some of the energy also goes into heat. Heat between the object and the surface that it's moving past. Whenever you have a resistive force, you are always going to be generating a non-useful type of energy like heat. This is sometimes referred to as wasted energy. In this example, we're told that the mass of the object is 2.5 kilograms, and the final velocity is 4 meters per second. We should be able to work out the value of the frictional force using this information. We remember that work is equal to force times by distance, and it's this force that we're trying to calculate. Remember that we are trying to calculate the resistive force, but that will have the same value, the same magnitude as the component going down the slope. So there's several ways that we can attempt this. I'm going to do it using the conservation of energy method. So we know that we're going to start with gravitational potential energy, and then that is going to become kinetic and heat energy. So the total gravitational potential energy that we start with is going to be equal to the kinetic energy that we finish with plus any wasted energy. And it will be in the form of heat. And that heat will be generated by the resistive force times by the distance that it moves through. So let's calculate the wasted energy, and then we'll have this value over here. The mass is 2.5 kilograms. Gravity has a value of 9.81, and the height above the surface of the Earth is 3 meters. We're told the velocity at the bottom of the slope, 4 meters per second. Remember that kinetic energy is a scalar. Rearrange this equation for the wasted energy. And do the calculations, and you'll find that the amount of wasted energy is 53.575 joules. So the heat that's generated by this drag force is equal to this value. And it's caused by work being done over a distance. The object has slid down the slope the whole length, so the distance is 5 meters. So the work done is this value here, and it's caused by a force moving through a distance. So let's rearrange for force, and we do a quick calculation to get our answer, which is approximately 11 newtons. Another way that we can study the conservation of energy is by doing this experiment here, where we have chemical energy stored in food being burnt. That means that we are changing the chemical energy into heat or thermal energy. That thermal energy is being used to heat up the water. Now, if we know the temperature change of the water and we know the mass of the water, then we can calculate the amount of energy that's been added to the water. And that will allow us to look back and see how much energy, chemical energy, was stored in the food. And this experimental setup is known as a calorimeter. Calorimeter as in calories, as in what you will read on a food packet. We know how much energy was stored in the food because we've seen how much energy was given to the water. You must be careful, though, to try to limit the amount of energy that is given off into the environment, because then it wouldn't be a fair test. And calorimeters typically have a lot of insulation built around them.